Welcome everybody to lecture 5 in fuzzy systems. Uh, Today we are going to begin with a new topic in fuzzy system called defuzzification. Last time we have taken the method of fuzzification in which we can convert any absolute variable in the environment to a fuzzy variable by means of human perception. Now we are going to make the opposite by defuzzification, in which we are going to convert a fuzzy quantity to a crisp quantity. And we have mentioned before that a crisp quantity is a classical absolute quantity that can be measured in the environment. Today, we can represent this process with the shown block diagram. As an input in this defuzzification block comes the fuzzy values, and the crisp quantity comes as an output from this block. Such a method can also be called a rounding off method. By this way, we can reduce a collection of membership function into a single scalar quantity. First of all, the first point in this lecture, we have to define what is called by lambda cuts. Lambda cuts means that we can represent for a given set of elements in a fuzzy membership function, we can deduce the maximum output. So by considering a fuzzy set A, then the lambda cut can be denoted as A suffix lambda, where lambda ranges between 1 and 0. As we said before, that for a fuzzy quantity, the range can be, the quantity can be described in a given range, not an absolute value as for a crisp quantity. And this can be represented mathematically for set A lambda is the membership function mu A can be represented such that mu A is greater than or equal lambda. In other words, the value of lambda cut set is x. The same properties as we mentioned before in fuzzy sets, the properties can be applied for lambda cut sets such that fuzzy set A union fuzzy set B all have the value the cut set lambda cut set. This is equal to the crisp set A of lambda union crisp set B of lambda. Also, the intersection between fuzzy set A and fuzzy set B with lambda cut. This can be represented such that both the classical sets A lambda is intersection to B lambda, but we can find here that the complement of fuzzy set A of lambda is not equal to the complement of the classical set A of lambda. This is only for the value of lambda equals 0.5. For any lambda smaller than or equal to alpha, such that alpha varies between 0 and 1, we can say, in other words, that the classical set A of lambda is a subset or equal to A of lambda. The classical set A alpha is a subset or equal to A lambda, where the value of A0 will be the universe defined. This can be shown on this graph where the membership function mu is plotted. For this fuzzy set A, we can see that for a given value of lambda, for example, A 0.6, in this case, the amplitude should be in the range of 0.6, such that here is lambda is equal to 0.6. This means that the range lies between the two limits of the fuzzy set A from this point to this point. By the same way, for the given amplitude of lambda 0.3, we find that the range of the fuzzy set A, the range of elements lies between this point of intersection to this point of intersection. This means that the range of elements X of the fuzzy set A lies between this point to this point on the x-axis, which indicates that for this range we have the maximum value at the intersection points with the membership function, such that lambda is equal 0.3. And from the properties can be understood that standard set of operations on fuzzy sets is similar to the standard set of operations on lambda cut sets. We can find a big similarity between the lambda cut sets and the non-fuzzy sets we have mentioned before. The same properties can be applied for fuzzy relations, such that we have here R of lambda is equal to X, Y, such that the membership function mu R, where the two elements of X and Y are greater than or equal to lambda. The same properties, as mentioned before, can also be applied in case of lambda cut relations, where the fuzzy set R union fuzzy set S of lambda is equal to fuzzy set R of lambda union fuzzy set of lambda. 2. The fuzzy set of R intersection fuzzy set S of lambda is equal to the classical set R lambda intersection the classical set R lambda S lambda. 3. We find here that the complement of the fuzzy set R of lambda is not equal to the complement of fuzzy set R of lambda. 4th, for lambda is smaller than or equal to alpha, where alpha lies between 0 and 1, then R alpha is included or being a subset in R of lambda. Sorry, R of alpha is included in R of lambda. 0.4, the smaller value is 0.4. We put it as 0.4. In the next step, we compare all these values for the given elements from x1 to x5 with the lambda value, which is 0.2. So 0.1 is smaller than 0.2, so we put it as 0, 0.2 and 0.2, 1. 0.3 is greater than 0.2, then 1, 0.5 is greater than 0.2, so we put it as 1. 0.4 is greater than 0.2, so we put it as 1. After solving the example for lambda cuts, now we are going to extend the concept of defuzzification by presenting some methods in order to defuzzify, as we said, a fuzzy membership function and convert it at the end to a crisp absolute value. The output of such methods is simply an absolute value from this described fuzzy membership. For a fuzzy membership function, simply for a given some fuzzy sets as shown fuzzy set C1 and fuzzy set 2, we have here two different fuzzy sets. One is triangular fuzzy set and the other is a trapezoidal fuzzy set. In case of obtaining the entire fuzzy process, we take the union between the fuzzy set C1 and the fuzzy set C2. This means that taking the union, we pose the fuzzy sets together. We can find we have here an overlapping area, but at the end, pose the two fuzzy sets, construct at the end this result, which is a fuzzy membership that represent a combination between a trapezoidal fuzzy membership, which represents this part, and the other part is a triangular fuzzy set. At the end, we will deal with this combined fuzzy membership function. In order to defuzzify the given fuzzy membership function to an absolute value, we have to introduce 7 methods in detail. The first method is called the maximum membership method. The second one is the centroid method. The third one is the weighted average method. The fourth one is mean max membership. 5 is the center of sums. 6 is center of largest area. And 7 is first of maxima or last of maxima. Now we are going to introduce each method in details. The first method is the maximum membership method. The decified value can be obtained directly by obtaining the maximum value in this fuzzy membership function. So can someone here deduce from where is the maximum value of this membership function? Yes, it is 1. This is the maximum value. And simply at this maximum value for this fuzzy membership function, we simply project this point with a line directly on this z-axis and obtain z star. So z star simply represents the defuzzified value of this membership function. So what happens here? We directly obtain the defuzzified value z star directly from having the maximum value or the maximum amplitude of this fuzzy membership function. The maximum here is at 1, so this means this represents this point here, and simply project this point on the z-axis. We obtain directly z star, which represents in this case the defuzzified value. This method is also referred as the height method. In other words, the height method, we get also the maximum value of the fuzzy membership. So mu c z star is simply greater than mu c of z. This means we got here the highest value in this fuzzy membership function. Second method, which is called the centroid method. This is most widely used method and can also be called center of gravity or center of area method. So this can be calculated here using the integration of the fuzzy membership function. So we take the integration mu c of z multiplied by z dz. This completely is divided over the integration of the membership function dz. So the difference between numerator and denominator is simply in the numerator we multiply by z. So this means we have to get for all these straight lines the equation describing this line and multiply it by z, and at the end divide it on the integration of this membership function. This can be obtained numerically by calculating each equation for the given straight line. If this membership function is not described with a straight line, simply we have also to get the equation describing this function. So again, for the centroid method, we simply calculate the defuzzified value z star by simply calculating the integration of the membership function multiplied by z. And divide it on the integration of the membership function. The third method is the weighted average method. Such a method has the property that we can't use it for asymmetrical output membership function. What does this mean? This means if we have simply a membership function as given here, this membership function must be symmetrical membership function, otherwise this method can't be applied. So we can find here we have a triangular membership function that has we can see here this is the same distance as on the other sides. Both sides are equal, so we can get obtain here a symmetrical membership function for both the two functions. And for example, here we can directly calculate the weighted average by getting the value A multiplied by the maximum value of the membership function and adding it to the value B multiplied by 0.6, which is the maximum value of the other membership function, and dividing it by the maximum value and the maximum value. By this way, we can obtain the weighted average. This method again can be applied only on symmetrical membership function. The fourth method, which is the min-max membership function. Min-max, so we try to find the maximum value in the membership function, in this case here represented by this line, which is equal to 1. And the defuzzified value for this example can be calculated by having the two limits in which the maximum value is illustrated here from A to B. So we get A plus B and divide it by 2 because we have here only 2 points. So Z star is simply A plus B divided by 2, where A and B are the endpoints of the maximum membership range as shown in figure. The next method is the center of sums. The center of sums simply involves the algebraic sum of individual fuzzy sets. So we have here a triangular fuzzy set, and we have here a trapezoidal fuzzy set. So by having these fuzzy sets by overlapping on each other, we got here the result as of the two fuzzy sets together. We can find that the intersection area is this area which is hashed. One of the interesting things in this method that we calculate simply all the areas of this membership function. We can find by calculating when we take this individual membership function plus this individual membership function, we find that the intersection will be added twice, which one of the main characteristics of this method for having the defasified value z star. So this method is similar to the weighted average method, but in center of sums, the weights are the areas of the respective membership functions, whereas in the weighted average method, the weights are the individual membership values. So by having the defasified z star, we got the summation of the fuzzy membership value, and at the end we multiplied it with z bar, which is the distance to the centroid of each of the respective membership function. In the shown figure, we can find that z star lies in the area of intersection between both the two membership functions. Method is the center of largest area. The center of largest area in this example, if the output fuzzy set has at least two convex subregions, which here this region and this is the other region, then the center of gravity of the convex fuzzy subregion with the largest area is used to obtain the defasified value z star. This means, in other words, we calculate the area for each region, for each convex subregion. This is the first region, which is lined here with black line at the barrier, and this is the second region. So we calculate the area of this one and calculate the area of the first one here. And for the bigger area, we simply apply this formula for only the largest area, which is the integration of the given membership function multiplied by z divided by the integration of the membership function. This resembles simply the same method before, but in this case we consider only the largest area. The last method, which is the seventh method, we simply consider only the maximum value for a given membership function, and if this maximum value is represented with a constant value represented by a line, for example, we consider the first of maximum and the last of maximum. What does this mean? We can see in this shown membership function, we have the first membership function given as a trapezoid. The second membership function is given as a triangle. So the maximum value in post membership function is simply this point, which is the vertex of the triangle. This is the maximum value. So we have only here one value at this maximum point. So the first of maximum and the last of maximum is only represented with one point, which is this point. So we can directly, without using mathematics, from the figure we can get it as z star is equal to 8, which lies directly from the projection of this point on the z-axis. So for the largest height, we simply calculate the height of this membership function, which is equal to sub of mu c k of z. And in case we have other membership function in which the maximum value is represented by a line like this, so we consider this is the first of maximum and this point is simply the last of maximum. And also this can be represented with the height directly from the z-axis. So it is very simple. Of our lecture with this presentation of the 7 methods and the lambda cut sets. Next time in the next lecture, we are going to have an example for applying these 7 methods. If anyone has questions and would like to discuss, he can send me an email on the LMS. I appreciate any comments of you. Thank you for your attention.